This is episode 3 of Real Analysis, a History. For 2 episodes we watched the 18th century, Euler especially, treat infinities like toys and get away with it. The answers were right, nobody could say why. By the 1820s, a Frenchman had had enough. His name was Cauchy. He didn't write fancier formulas. He did something that looked, at the time, like ruining the party. He took the words everyone used by feel, approaches, converges, and locked them down with inequalities. Today's twist: even this father of rigor left a hole, and that hole forced out the most important piece of all of analysis. Let me put it plainly, after 100 years of mathematicians winging it, one man showed up to ruin the party and accidentally built the foundation of all modern math. His real superpower wasn't a formula. He could tell you a sequence reaches a destination without ever telling you where the destination is. Here's the situation. Newton and Leibniz gave a powerful tool, Berkeley showed it didn't logically hold up, Euler just said use it and don't ask, shoving infinities around. For over a century the whole field ran on the intuition of top geniuses. Euler's gut was sharp, so he didn't crash. But math can't keep betting that the next person is also Euler. Cauchy's demand was one sentence: correctness can't depend on a genius's gut, it has to be checkable, step by step, by anyone. We casually say x gets closer and closer to 3. But what does closer and closer even mean? Cauchy's idea: drop the verb, make it a challenge. To say a sequence approaches L means, name any error you like, say 1,000th, I guarantee that from some term onward, every value differs from L by less than your number. Picture a band of width plus or minus epsilon around L. No matter how narrow you make the band, eventually all the points fall inside it. That's the whole test. Pick L, draw the band, if from some point on every term sits in it, and that works for every band however narrow, the sequence approaches L. Now try 1, 0, 1, 0, forever. Pick a band of width 0.1 around any candidate, the sequence keeps jumping out of it. It fits inside no narrow band, so it approaches nothing. Cauchy turned the fuzzy getting closer into an inequality anyone can check. That definition has a catch: you have to know L in advance to test it. But often you don't. An iteration, an infinite sum, you have no idea what it equals. So Cauchy pulled a genius move: stop measuring how far each term is from the finish, measure how far the terms are from each other. If, far enough out, any two terms can be made closer than any epsilon you name, the sequence has a destination even if you never learn what it is. That's a Cauchy sequence. Think of a crowd walking toward a meeting point hidden in fog. You can't see the point. But if you watch the crowd pack tighter and tighter together, you can be sure they're converging on something. Bunching up itself guarantees a home exists. Compare 1, 0, 1, 0, adjacent terms always differ by 1, they never bunch, so it's not Cauchy, and it diverges. For the first time, judging convergence didn't require knowing the answer first. Remember Euler's 1 minus 1 plus 1 minus 1? Its partial sums are 1, 0, 1, 0. Measure with Cauchy's new ruler: adjacent terms always differ by 1, they never bunch, so it is not a Cauchy sequence. Verdict: divergent, and what does it equal is not a legal question. The cowboy era was officially over. To be fair, this doesn't say Euler was wrong. Under a wider notion of summation it's still 1/2. Cauchy just nailed down ordinary convergence so nobody could wing it again. Now the twist. In his 1821 book, Cauchy wrote a theorem: add up continuous functions and the sum is continuous. Sounds obvious. But within a few years, Fourier's series produced a counterexample: a pile of smooth sine waves adding up to a square wave with a vertical jump. Continuous things sum to something discontinuous. Cauchy was wrong. The missing ingredient: the functions don't just each have to converge, they have to converge in step. Pointwise convergence means, for each x, the values do approach the target, but some x's converge fast, some slow, nobody's in sync. Uniform convergence means, all the x's must enter the plus or minus epsilon band together, nobody left behind. It's the difference between a class where everyone hands in whenever they finish, versus everyone handing in at the same deadline. Only the in-sync version keeps continuous summing to continuous, exactly the condition Cauchy missed. Even the father of rigor missing it shows how subtle it is. Cauchy's ruler, judge convergence without knowing the finish, is the lifeblood of modern computing. Any iterative algorithm, solving equations, training models, rendering, simulating, doesn't know the final answer. How does it decide done, stop? The Cauchy criterion, when two consecutive steps differ by less than some epsilon, declare convergence and halt. Gradient descent stopping rules, numerical convergence checks under the hood, that's all Cauchy. Cauchy's sequence leads straight to the idea of completeness, a space where every Cauchy sequence really does have a home. And completeness is the shared foundation of Banach and Hilbert spaces, of fixed-point theorems, of the existence of solutions to differential equations, even of convergence proofs in machine learning. A concept invented in 1821 to ruin the party is now a load-bearing wall of the entire edifice of modern computation. Beyond the present, completeness keeps opening frontiers. The contraction mapping principle, in a complete space, a contraction has a unique fixed point underpins why diffusion models, reinforcement learning, and many solvers converge to a unique answer. There's also a different way to fill the holes, change how you measure closeness, complete the rationals differently, and you get the p-adic numbers, a frontier tool in number theory and cryptography. And the hard guarantees of numerical analysis, error bounds, convergence rates, stability, all speak this Cauchy completeness language. Cauchy's machinery is exactly the limits and continuity weaks of every analysis course. They pin approaches to the epsilon challenge, Cauchy seeded it, Weierstrass nailed it. They introduce Cauchy sequences to judge convergence without the limit, then use them to build the real numbers and define complete spaces. They make completeness every Cauchy sequence converges, the axiom that separates the rails from the rationals. And they teach uniform versus pointwise convergence, Cauchy's famous gap, because only uniform convergence preserves continuity and lets you differentiate and integrate term by term. Cambridge's Analysis I, Princeton's M8215, and MIT's 18.100 all treat this as the first gate into the subject. One line to take away: Cauchy's gift wasn't a formula, it was a ruler that knows you'll arrive without ever seeing the destination. 3 takeaways. 1. Approaches L means surviving every epsilon band from some term on. 2. A Cauchy sequence proves a limit exists without naming it. 3. Even the father of rigor missed uniform convergence. Rigor itself needs patching. But here's the cliffhanger. Cauchy promised that a bunching sequence always has a home. What if your number line has a hole right where the home should be? 1, 1.4, 1.41, 1.414, bunching beautifully but heading for the square root of 2, which isn't a fraction at all. On the rationals, that sequence falls through a gap. So before Cauchy's promise can hold, someone has to fill every hole in the line. What is a real number, really? Next episode, Dedekind and Cantor rebuild the entire number line from scratch. If you like math told as a thriller, like and subscribe for episode 4. That's the whole of episode 3 of Real Analysis, a History.